Welcome to this video on reinforced polymers. We will look at the use of fiber-reinforced polymers, or FRP, in structural elements and explore their many advantages in modern construction. In this video, we will cover the advantages of reinforced polymers, the different types available, their practical application on various structural elements, and why they are so beneficial for construction projects. FRPs have gained wide acceptance in civil engineering and construction. Their high strength-to-weight ratio, corrosion resistance, and ease of application make them ideal for strengthening and protecting structural elements like beams, columns, bridges, and more. Fiber-reinforced polymers, FRP, provide a powerful solution for strengthening structural beams. The main purpose of using FRP is to significantly increase flexural strength, stiffness, and fatigue resistance in key structural components. In practice, high-performance FRP sheets, strips, or laminates are securely bonded directly to the tension face or sides of beams using structural epoxy adhesives. This modern application offers several major advantages over traditional methods. It effectively prevents cracking and failure under heavy bending loads while remaining lightweight and minimally invasive compared to traditional steel plate bonding. Ultimately, FRP retrofitting enhances load carrying capacity and extends overall service life. FRP for columns, structural applications. Moving to columns, fiber-reinforced polymers play a critical role in structural retrofitting. The primary purpose of using FRP here is to improve axial load capacity and confinement, significantly enhancing both overall ductility and strength. In application, continuous FRP wraps or composite jackets are wrapped securely around the perimeter of the column. This technique delivers key structural benefits. It increases compressive strength and deformation capacity, while providing essential confinement to the concrete that delays structural failure. Additionally, it protects the internal steel reinforcement from environmental corrosion, ensuring long-term durability. FRP for slabs and floors, structural applications. Next, let's examine FRP applications for slabs and floors. The main purpose of using fiber-reinforced polymers in these elements is to increase overall load capacity and control cracking under service loads. In practice, high-strength FRP laminates or flexible fabrics are applied directly to the bottom or top surface of slabs, depending on whether positive or negative bending moments are targeted. This system provides major structural benefits. It improves flexural strength and fatigue life while effectively rehabilitating damaged or deteriorated slabs. Additionally, applying FRP reduces deflections and increases overall stiffness, significantly enhancing performance and durability. FRP for walls and shear walls, structural applications. Turning to walls and shear walls, fiber-reinforced polymers serve a vital role in structural stability. The primary purpose of applying FRP in these elements is to enhance shear strength and ductility. In practice, high-strength FRP sheets or flexible fabrics are bonded directly onto the surface of the walls. This installation provides several critical benefits. It significantly increases resistance to lateral loads caused by severe wind or earthquakes. Furthermore, it prevents shear cracking and brittle failure, making FRP an exceptionally useful and reliable material for the seismic retrofitting of buildings. FRP for foundations and footings, structural applications. Moving on to foundations and footings, fiber-reinforced polymers provide critical support below grade. The primary purpose of applying FRP in foundation systems is to improve overall load distribution and prevent cracking under structural stress. In terms of application, FRP materials can be embedded directly within concrete or wrapped securely around key foundation elements. This approach yields substantial long-term benefits. It significantly enhances durability against aggressive soil environments, reduces maintenance costs by protecting internal steel from corrosion, and ultimately increases overall structural integrity for the entire building. FRP for bridges and infrastructure, structural applications. Turning to bridges and major infrastructure, fiber-reinforced polymers are playing an increasingly crucial role. The main purpose of using FRP in these large-scale systems is to efficiently repair, strengthen, and protect critical elements like bridge decks, girders, and piers. For application, FRP laminates, sheets, or reinforcing rods can be externally bonded to existing surfaces or used as internal reinforcement. This delivers substantial practical benefits. It significantly reduces overall weight while improving corrosion resistance compared to traditional steel. Furthermore, FRP retrofitting extends the service life of aging infrastructure and allows for rapid repairs with minimal traffic disruption. FRP in seismic retrofitting, structural applications. Finally, let's look at FRP in seismic retrofitting. The primary purpose of using fiber-reinforced polymers here is to upgrade the overall seismic performance of structures by significantly increasing strength, ductility, and energy dissipation capacity. In application, targeted FRP confinement is applied directly to columns and shear walls to improve their flexural and shear capacities. This strategy delivers essential benefits during major earthquake events. It provides critical structural confinement to columns and shear walls, improves overall flexural and shear resistance, and significantly increases energy dissipation during seismic activity, preserving stability when it matters most. Advantages of using FRP on structural elements. Fiber-reinforced polymers offer key advantages over traditional materials for structural applications. First, FRP features an exceptionally high strength-to-weight ratio, adding substantial reinforcement without increasing dead load. Second, its superior corrosion resistance dramatically extends durability, particularly in harsh or aggressive environments. Third, the material allows for easy and fast installation, causing minimal disruption to building occupants or traffic flow during retrofitting. Fourth, FRP is non-magnetic and non-conductive, making it ideal for sensitive electrical or specialized facility environments. Finally, it is highly versatile and adaptable, conforming seamlessly to a wide range of structural shapes and sizes. Conclusion: built to perform, built to last. In conclusion, fiber-reinforced polymers are truly built to perform and built to last. Today, FRP is extensively used across the construction industry due to its high strength, lightweight nature, corrosion resistance, and exceptional versatility. Ultimately, FRP materials have transformed how we approach both new builds and the repair of existing infrastructure. By offering superior durability, significant weight savings, and long-term efficiency, FRP has become a vital component for sustainable, resilient, and innovative civil engineering projects around the world. Thank you for your attention.